All right, how's everyone doing? Get bonus points for being here today. So, any questions? So PA4 looked good. Biggest challenges were delete and memory issues, which is not surprising or particularly worrisome. Delete is nailing every detail down, and if anything's off, usually things don't work very well. But I tried just deleting a few nodes from a small tree and then traversing and making sure the traversal order was what I expected. Also tried deleting everything in the tree to make sure that works, and that's a bit of an edge case. And then ran it through Valgrind, and it was looking for no warnings, no memory leaks from Valgrind. And a lot of people were able to get that, which is great. So PA5, doesn't really get heavy on data structures per se. It's more an algorithms kind of thing, doing dynamic programming and heavy recursion. But we'll get back into more data structures in 223 for sure. We're going to talk about tries today, and then we're going to start talking about sorts. And sorts don't really have to do with data structures per se. That's another algorithm kind of thing until we get to heaps. And then heaps will be related to sorting, and there'll be another type of data structure. So any questions on PA4, PA5, anything else before we start? All right, so let's talk about tries. So tries are these really wide trees. With binary trees, we have nodes where each node has a piece of data and two children. In a try, and we're gonna work with a restricted case, so we're just gonna work with words with uppercase letters only. So no spaces, punctuations, lowercase, etc. In this case, in the try, each node has up to 26 children, and it has not really a piece of data, but it has a bit, which we call end of string, so it's a flag. Typically it would be, a short integer or a character or something like that. We can just think of it as a Boolean. So 26 children and an end of string flag. And here's a node. And the way I want you to think about this is if I don't indicate otherwise, EOS is set to a 0. This flag is turned off. And if I don't show anything coming off of these 26 pointers, these pointers are null. Okay, so they're not pointing to any children. And so in an empty try, our root would look like this. And there's no pointers to anything other than null, and end of string is set to 0. And so this is an empty try. It's just one node. Okay, so let's store a word in here. Let's store the word OK. Go ahead and just pass it around because a few people came in late. Thanks. Okay, so how do we store the word OK in this try? Well, here's the thing. We start from the root and we find the first letter O. We find that node in this collection of nodes. And since O is pointing to null, it means we don't have anything in our try that starts with an O. So we're going to create a new node, and we're going to have the O point to that new node. Okay, that's our first letter, O. The second letter is K, so we're going to go over to the pointer corresponding to K, and that's pointing to null right now. So we're going to create a new node and have the K point to that new node. And now we've stored OK, and so the node that's being pointed to by the K, we're going to set this bit end of string to be a 1. And that's going to indicate that the word OK is part of our try. Yeah, I got it. All right, so we have one word in our try, OK. Okay, now let's store a cat in our try. So first word is a C. We're going to go to our root. We're going to look at the C pointer. That's null right now. So we're going to create a new node, and we're going to have that C point to the new node. That takes care of the first letter. Second letter is A. We're going to take that node we just created. We're going to look at the A pointer. That's null. So we're going to create a new node, have the A pointer point to that. Now we're at our third letter, T. We're going to look at the T node in that new node. That's null, so we're going to create a new node, have the T point to that. And then since that's the last letter of the word, we're going to set this end of string bit to be a 1. And now we have a cat in our try. Okay, let's store cats with an S. Start of the root node, look for the pointer from C. That's not null, it's pointing somewhere. So let's follow that over here. It points to this node. Second letter is an A. The A is not null, it's pointing somewhere. So we'll follow that to another node. Third letter is T. T is not null, it's pointing somewhere. So we'll follow that to another node. Fourth letter is S. S is null. So we're going to create a new node. We're going to have S point to that. And now we're at the end of our string, so we mark the end of string bit to be a 1. Okay, so a few things here. First of all, we always start from the root. Each node in here is either null or it's pointing to another node. It can only point to one node, though. It can't point to multiple nodes. We set end of string after we followed the pointer for the last letter. So O takes us down here, K takes us down here. That's where we set the end of string for the word OK. If I set the end of string pointer right here, what word have I just added to my try? If I set end of string right here, I've added the single character O. Because how do I add an O? I'll start in the root, take the O that points to a node, set the end of string in that node. Okay, let's put a dog in. Start at the root. Find a pointer for D. That's null, so make a new node. I'll use this one down here. And point to that. Second letter is O. That's null, so point to a new node. Last letter is G. That's null, so point to a new node. The end of string bit to a 1. Now we got a dog. So if we drew this the way that we normally draw trees, all right, here's an O, and it points to a node, and there's a K, and that's got an end of string bit set, which means that's a leaf node. Here's our C, which points to another node with an A, which points to another node with a T, which points to end of string, but also points to another node with an S. And here's a D, which points to an O, and so on. So I mean, you can picture this as a very wide tree where each of these nodes is 26 across and can have 26 children. But I'm drawing it like this because it's easier to put on a piece of paper. One thing that's interesting about this is the word cat is not stored anywhere. Right? There's no data field in these nodes where I store CAT or DOG. It's different from a binary tree, for example, where we actually have a field called data that has the number. The fact that the word cat is part of this trie is an artifact of a path you can take to a node where end of string is set. We can follow the C link, the A link, and the T link. That's the reason that cat is part of the trie. So that's a little quirky. So how efficient is this time-wise? Suppose I have a gazillion things in my trie. I have like every word in the dictionary stored in my trie. How much work do I have to do to find the word cat?
3 or 4 checks?
3 or 4 checks, that's it. If my longest word is 15 letters, it takes me 15 checks, 15 operations to find any word, no matter how full my trie is. So time-wise, it's pretty efficient. But what about space? Yeah. Space-wise, it's really a space hog. Because every time I put a letter in, I've got 26 of these pointers. These are typically 8 bytes times 26, and then another byte at least for the end of string. So it takes a lot of space. And this is a typical trade-off we can play in computer science engineering. And you can think of the design area with 2 dimensions, one axis representing space consumption, the other axis representing time consumption. And where would we like to be? We'd like to be over here. We'd like algorithms that take no memory and no time. That would be cool, right? If you store your data in an array, and it's just a consecutive set of locations in memory, right? That's a pretty minimal amount of space and a pretty high amount of time. So this might be an array. If you have a trie, it takes a lot of space, but it's pretty efficient time-wise. And it's like there's some kind of, cloud of possible algorithms, possible solutions that we can explore. But what we'd really like to do is come up with designs that are somewhere down around here, low space, low time. What we want to avoid is designs that take a lot of space and a lot of time. But we're largely constrained to some sort of diagonal in here. Alright, so tries are a different point in this space-time graph. All right, so let's play with this, because you'll definitely see one of these on the exam. So let me pass out a worksheet. And let's go ahead and put some stuff into here and play around with the structure. And these are pretty harmless to code, yeah. There's stories about why it's called a try, and I don't know which ones are true, but there is a lot of folklore around it. And I think it was Fredkin who coined the term. Fredkin as in reversible computing. But yeah.
Could it be that some of the first tries were just trees with 3 child nodes, and that might be why, part of why?
That could be. And now we gotta go look. And the definitive source for all knowledge is Wikipedia, right? Fredkin coined the term. He pronounced it as tree after the middle syllable of retrieval. There you go. But we call them tries to keep them different from trees. But I don't know if that's true or not. Fredkin's an interesting person to look up if you want to spend an afternoon down a rabbit hole. In particular with respect to something called reversible computing, which is the idea that when you do like a logical AND operation, you lose information. If you know that ANDing 2 bits gave you a 0, you could have had 2 zeros or a 0 and a 1 or a 1 and a 0 to begin with. You don't know what the inputs were, you just know that the result was a 0. So you've lost information, you've destroyed information. And in information theory, there's a notion that destroying information generates heat. And so every time you do one of these irreversible computations, you generate a little bit of heat. And it's minuscule compared to the heat of running, current through wires or switching a transistor, but the concern of Fredkin and others was that as our computing got more and more efficient, the amount of energy we spend running current through wires and switching transistors could get smaller and smaller. If you have superconducting wires, you have no resistance, so that goes away. But the heat you generate from destroying information is always a certain non-zero amount. And eventually our physics would get to the point where the dominant cause of heat was this destruction of information. And that from a information theoretic viewpoint, you can't do anything about that if you're destroying information through these irreversible operations. So he started exploring this idea of reversible computing, which would mean that theoretically, once you had your answer, you also had everything you needed to go back to the original question. And the hope was to be able to bring that heat from information loss down to 0. And then theoretically, as your physics gets better, your total heat in the system can get arbitrarily small. And this is when you're thinking like nanotechnology, where you have a trillion transistors switching inside, a little cube of computing goo, and heat's a big issue.
Why not just store those values in variable?
Well, that's one way to do it. So there's like a Fredkin gate, and it basically preserves the inputs in some way. But it can be a storage problem. So yeah, it's a fun rabbit hole to explore if you're interested in theoretical computing, or just want to do something other than tries, All right, so let's store some things in our try. So start off, let's store an ant. So your root's always going to be the same, and I'd say let's just make it this first node, and we've always got to start from there. So remember the basic drill, start with the first letter. If that's pointing to null, make a new node pointing to that, and then branch off the second letter and so on. And so the T has to point to a new node, and then in that new node you want to set end of string. Because if we had something else that began with AN, like AND, we need to be able to know that that's also part of the structure. And another thing is, remember, these pointers are actually pointing to the entire node, not just to a letter in a node. So they point to the whole node, and then in that node we set the pointer associated with a letter to point somewhere else, or we set the end of the string. That's okay. So have that go to another node and set under string that node. Cool. All right, so yeah, A will point to a new node, N points to another node, T points to another node, and then that node set the end of string to 1. So again, there's no notion of having this N point to the T, for example, right? This is a node, we just point to the beginning of the node. Yeah?
So would the node be like a structure?
Yeah, it's a struct node with 27 fields. Yep, exactly. All right, and then the end of string has to be right here, because if you put the end of string here, I've said that AN is part of my trie. So how do we add AND?
Have a node stem off a D after AN.
Mm-hmm. Yep. So A comes down here, there's our N points there. Bring a node off of the D. And since it's null right now, we're going to create a new node, point to that one, and then in that one, since that's the end of the string, we'll set EOS to 1.
That can't be the same one that T.
But it can't be the same one that T is pointing to.
So sorry if this has already been addressed, but with like ant, if you wanted to spin off like anti,
Mm-hmm.
would you like to make a new node that points to T and then one after that that points to I?
So let's do ANTI. So start with the A, that takes you to the second node is an N, takes you to the third node is an T, takes you to this fourth node. I is null, so we'll make a new node and have I point to that new node. And then in there we'll set end of string.
So end of string is just saying that this could be where.
End of string is saying there's a word that ends right here, so this is actually anti. And this, I should have done this as we went. This was AND. And this was ANT. Okay, so what about go? started the root, but the G, since it's null to begin with, I'll get you a new node. And build in there, yeah, exactly. Yeah, it takes lots of nodes. Is that what you mean? Yep. So yeah, so G's full of this because if you come down here and then you come off with O, well now you got the word A followed by O as part of your try. Yeah. That's good. All right, so the trick here is the G, if I were to point it at some pre-existing node like this node right here, I'm saying that there's a G followed by a D as part of my word, right, part of my try. And if I point my G to this second node, I've got a G followed by an N followed by a D as part of my try. So when you're adding a word, if G is currently null, you don't want to point it to a pre-existing node, right? Because each of these pre-existing nodes has some other piece of a word in it. So we'll point it to a new node, and then just continue through the letters, and then set the end of string at the end. All right, so that's basically tries. Very efficient for storing, very efficient for retrieving. A little problematic to search, or to delete, because you can just clear out the end of string to remove a word, but if you really want to reclaim space, you need to do some work to know if you can actually free the node, right? So if I get rid of the word go, I know I can set this end of string to a 0, and since all of these are null, I can return this to the memory pool, but I have to return the thing that was pointing to it to be null. And if all of these are null and end of string is 0, I can free this from the memory pool, but the thing that was pointing to it I have to set to null. So it takes a little bit of work to delete, but it's really efficient if you just want to throw a bunch of things in and then just be able to access them efficiently. All right, so you'll probably see this on your final exam, a worksheet like that, and just adding some words and seeing if some words are in the structure. So that's one thing you don't have to study now. All right, any other questions about that? All right, well, let's talk about sorting and searching. And there's a variety of ways to sort data. There's the famous bubble sort that we all know and love. There's an insertion sort. There's a selection sort. There's merge sort, quick sort, heap sort, radix sort. And there's some others. You can find whole books on sorting. Why do we have so many different ways of sorting things? So after about, I don't know how many years of teaching here at Clark, I was doing this lecture and I started wondering, like, how do I sort papers? And it turns out I do an insertion sort usually when I'm alphabetizing papers, depending on how big the class is. If the class is really big, I end up doing a merge sort. And I'd never thought about it. I never sat down and you know, looked up sorting algorithms and decided what to do. It's just what I was doing. I don't know anybody who just sort of arbitrarily does a bubble sort. when they're sorting papers or, coins or whatever. So yeah, why do we have so many different kinds of sorts? You had your hand up.
We have many different types of data structures.
Yeah.
that have different needs.
We have lots of different types of data structures, different types of data. And different types of data work really well or not so well for different kinds of sorts. There's also the efficiency of sorts. So, bubble sort, insertion sort, selection sort, they're easy to code. They're simple algorithms, but they have what we call order n squared performance. And order n squared basically means they're slow. It means when the amount of data increases, the performance gets really bad. And I'll make that precise in a minute. Merge sort, quick sort, heap sort have an order of what we would call n log n. And that's generally better. Radix sort nominally has something like order n, which seems even better. So I want to talk about these orders of complexity because we'll use this as we're going through talking about sorts. We use this when we talked about arrays and lists and trees a little bit. And in a algorithms course, you'll spend a lot of time talking about what these things mean, and big O versus little o versus theta, and best case, average case, worst case, and all kinds of analysis like that. But I want to give you a basic overview of what these orders of complexity mean. So let me give you a hypothetical analysis of some algorithm. So amount of data n. So let's say we have an algorithm where we run it for 10 pieces of data and 100 pieces of data and 1,000 pieces of data. And we look at how much time it takes in, I don't know, microseconds, milliseconds, weeks, whatever time unit you have. And let's suppose that when we run this algorithm on 10 pieces of data, suppose it's a sort, right? Suppose it takes 1 unit of time. And suppose when we run it on 100 pieces of data, it takes 10 units of time. And when we run it on 1,000 pieces of data, it takes 100 units of time. And let's say when we do 20 pieces of data, it takes 2 units of time. Okay, so what's happening here? When I increase the amount of data by 10x, the amount of time goes up by 10x. From 100 to 1,000 is 10x, from 10 to 100 is 10x. From 10 to 1,000, that's a 100x increase in data. The time went from 1 to 100, that's a 100x increase in data. When I went from 10 pieces of data to 20, I doubled the amount of data. What happened to the time? It doubled. Okay, so this is what we would typically call an order n, which is our way of saying that the growth in time complexity is linear with the growth in the size of the data. Double the amount of data, double the amount of time. Okay, order n is nice. You kind of expect if you're going to process twice as much data, it's going to take more work. If it only takes you twice as much work, that's pretty good. Okay, that's like, washing a car takes an hour, washing 5 cars takes 5 hours. That's linear performance. Okay, suppose that 10 pieces of data takes you 2 units of time, and 100 pieces of data takes you 200 units of time. And 1,000 pieces of data takes you 20,000 units of time. And 20 pieces of data takes you 4 units of time. Okay, what's happening here, you double the amount of data from 10 to 20. you square the amount of time from 2 to 4. When you increase the amount of data 10x, your computation time goes up by 100x. Actually, this should be an 8. Okay, 10 times as much data, 100 times as much time. 100 times as much data, 10,000 times as much computation required. So this is what we call order n squared, or quadratic performance. Order n squared means roughly if you double the amount of data, you quadruple the amount of time required. And you may have, you know, a really nice algorithm, which if you measure it on the wall clock, takes 1/5 as much time as this original algorithm. To do your algorithm on 10 pieces of data, it used to take a microsecond, and now it takes 0.2 microseconds. That seems like a good algorithm. It seems like an improvement. But when you get to 100 pieces of data, you'll find that your time is twice what it used to be with your old algorithm. When you get to 1,000 pieces of data, your time is 20 times longer than the old algorithm, right? Even though your algorithm may have been quicker on a small amount of data, the growth of that time requirement is n squared versus n. Eventually, that's going to overwhelm this small increase in the actual wall time, and your n squared algorithm is going to be slower.
You already go with your amount of data, you could still use the n squared.
Yeah, if you're not going to work on 1,000 pieces of data, if you're never going to work on more than 10, go with this. All right, that's going to be more efficient. But if your problem is likely to go up to 1 million pieces of data, this is going to be way, way, way slower than your order n algorithm. Even though, you know, for a small amount of data, order n took longer. So we're looking at asymptotic limits here. Okay, we're looking at as the amount of data grows towards infinity, what is the expression that dominates the time that's required? Is it n? Is it n squared? Is it something in between? Is it something worse than n squared? Yeah.
Are there some algorithms that are 2 to the n or is it coefficient?
Sure. Yeah. Yeah. Yeah, things can get a lot worse than this. So one thing we can do when we're calculating these orders of complexity, we can do a lot of sloppy calculation, right? This is really showing that you know, order n squared over 10 is really the same thing as order n squared, right? As n gets bigger and bigger, let me make you a new table. So here's n squared, here's n squared over, let's just do it over 2. Okay, so here's standard order n squared behavior, right? 10 times as much data, 100 times as much computation, 100 times as much data, 10,000 times as much computation. Okay, if this is, let me do 2n squared so we don't have to divide. If the time that an algorithm takes is actually twice n squared, this will be 2, this will be 200, this will be 20,000. The increase from here to here is still 100x. The increase from here to here is still 10,000x. Right? So increase the data amount by 10, you increase the computation by 100. Increase the data by 100, you increase the computation by 10,000, 100 squared. Okay? This constant factor doesn't change that analysis. So when we're calculating the order of complexity of an algorithm, if we get 2n squared or n squared divided by 5, it's still order n squared. Okay, these constants go away basically. So classic bubble sort. Classic bubble sort is a pair of nested loops. We have n passes that we make through our data, that's the outer loop. And the inner loop says run through all n pieces of data, compare element j with element j plus 1. If they're out of order, swap them. All right, so we move through our array and we swap pairs. And when we get through this inner loop, we know that we have one piece of data in the correct position, the largest one. And so after we make n passes, all n pieces of data are in the correct position. And this is clearly n squared, right? This inner piece of the loop will happen n squared times. And it may be that your data is in order to begin with and we never have to swap. Or it may be that your data is completely out of order and we have to swap every single time. So the amount of work you do could be, n squared times 1. It could be n squared times 6. Right? But they're both going to be order n squared. And if you do a fancier bubble sort, since we know that each pass moves one piece of data into the correct position, we don't need to go through the entire array each pass. We can go up to, say, n minus the pass number. And the amount of work you're going to do here, if, say, n equals 10, is going to be 10 plus 9 plus 8. So it's going to be something like n squared plus n over 2. But that's still order n squared. Right? The divided by 2 doesn't affect us. And if you just look at n squared plus n, as n gets closer and closer to infinity, this gets closer and closer to n squared. Right? 1 squared plus 1 is very different from 1 squared. It's twice as big. 1,000,000 squared plus 1,000,000 is almost the same as 1,000,000 squared. It differs in, a tiny little percentage of the value. So we can be sloppy when we do these orders of complexity. So order n squared is undesirable. Order n cubed is even worse. If you had 3 nested loops, that's typically going to be order n cubed. Let me leave you with a classic problem called traveling salesperson problem. So you have a series of cities. And you have connections between every city and every other city. And you have distances between each pair of cities. And your question is, starting from some city, how can I visit every other city and come back to my starting point in the shortest amount of distance? So I could go to B and then go to D and then F and E and C and go back. Or maybe I want to go to B and D and, if this is 12, I could go back to A and come over to C. That's only going to take me 5. That may be the best way to get to C. And this is possibly the most heavily studied problem in computer science. It's a favorite of people who aren't computer scientists per se, but know a little bit about computers. People will spend a lot of time trying to come up with algorithms for this. It's an easy problem to solve if you don't care about speed, right? If you have n nodes, n cities, or maybe n plus 1, well, start at your city A. You only have n other cities that you can possibly visit, right? I could go to city B, C, D, E, F, right? I have n choices to make. And once I get to whichever city I go to next, I have n cities I can go to. And once I go to that city, I have n choices, right? And if I'm only going to visit a total of n cities, this is just n to the nth possibilities. And n nested for loops will let me explore that entire space. And so inside those n nested for loops, I simply add up the distances that each of those for loop variables corresponds to, and whatever that total distance is I get, if that's better than my best solution, I save that as my new best. And at the end of iterating, I'll have my shortest distance. But this is, oh, that's bad. This is order n to the n. Yeah, which is a lot worse than n squared or n cubed. If you can find a solution to this that's order n squared or n cubed or n to the 10th, or if you can find a solution of this that's order n to any fixed integer, right, you're going to be famous and a little rich. Right, there's like $1 million prize for that, and all kinds of upsetting of computer science as we know it. So that's something we'll get into at the end of 215 this quarter. All right, so tomorrow we will hopefully talk about sorts. We'll start talking about details of some of the different versions of sorts and comparing their performance.